Hello, my name is Morgan Hordinski, and I'm working with John Will and Dr. James Brooks. The focus of our research is on human trust in automated systems. As automation systems become more prevalent in the world, the need to understand and improve the interaction between human operators and these systems is becoming increasingly important. Our research explores the hypothesis that a human operator trusts an automation system more when its design dynamic behavior is similar to the operator's manual control of that system. The goal of this research is to explore that connection between trust and automation in the context of an overhead crane system. The results of this research have implications in the future design of automation systems. To explore this hypothesis, the first phase of the study seeks to understand how people assess crane performance by examining the control system behaviors that people perceive as being similar and the specific factors which lead them to draw conclusions about crane performance. We designed the study to be a survey with 40 videos, each displaying a pair of simulated cranes moving from the same starting position to a destination. To design the crane trajectories, we utilized the equation shown. This equation allowed us to choose a desired trajectory for the load and calculate the carriage trajectory necessary to produce the load trajectory. There were a total of 16 control systems, with the load having either a damped second order or sigmoid-shaped response. Each control system exhibited a variety of performance characteristics. The two graphs show examples of the types of trajectories of both the carriage and the load calculated from this equation. The table on the right shows the varied parameters across the 16 systems used in the survey. The video shown on the bottom right is an example of the crane simulations that were used in the survey. To understand people's perceptions of crane performance, after watching a pair of crane trajectory videos, each subject ranked how similar the two videos were, and subsequently indicated which crane trajectory they preferred. These figures show the relative performance ratings for each of the performance parameters that we examined: rise time, settling time, peak time, and percent overshoot. From these four performance characteristics, rise time and peak time were associated with increased preference, while percent overshoot and settling time were associated with decreased preference. Additionally, on average, the subjects preferred the sigmoid trajectories over the damped second-order trajectories. Both these results and the subjects' comments suggest that the percent overshoot of the crane load is the principal way in which subjects perceive crane performance and similarity. The next portion of our study will focus on implementing a crane model to compare one's trust in a control system with one's manual performance based on the amount of overshoot that the system has. The block diagram on the right shows the design of the simulated system that we used in the first portion of study, and the figure on the left shows the validity of the simulated crane model by comparing its trajectory to that of the physical crane model. I will have John show how the physical crane model works.
Hi, I'm John Will. The crane system shown here was constructed using a 2-axis plotting device mounted on an aluminum frame. We track the movement of the carriage using an ultrasonic range sensor and measure the angle of the swinging load cable using a magnetic encoder that tracks the rotation of a magnet mounted on the cable. The system is controlled by a PC running Simulink that uses a MATLAB S function to pass commands over USB to the plotting device. The commands are determined either manually with a joystick or by an automated control system. Thank you.